An array is a type of data structure that stores a collection of elements in a contiguous block of memory, which means that the memory addresses assigned to its elements are all together in the contiguous sequence, something like this, and not scattered like this. Each element in the array is identified by an index starting from 0. Now, the first memory address of the array is known as the base address. In this example, it's 100. And the gap between the memory addresses is 4 units, which means that each element takes 4 units of memory. Also, each element of the array should be of the same size and data type. This contiguous nature of arrays makes accessing the elements very fast. We can access any element in constant time using this formula. The address of element equals base address plus index times size of each element. So let's say you want to find out the memory address of the element at 4th index. You can simply use the formula where the base address is 100, the index value is 4, and the size of each element is also 4. Calculating this will give you the memory address of the element at 4th index, ultimately getting the element at that address. Now updating any element is also very similar. First get the element's address in constant time and then assign the new value. Now the next operation is traversing the array and getting the values. So here n is the length of the array and we need to loop over the whole array once, and in each iteration print the value. Now arrays can either be static or dynamic. Static arrays have a fixed size that cannot be changed once set, while dynamic arrays can change size as needed. For now, let's consider this array to be static, with a size limit of 8. We will explore dynamic arrays in more detail later. Now the next operation is deleting the elements. So here we have a delete function with array and index to be deleted as the parameters. Now n is the length of the array, and then there is a condition that if index is less than 0 or index is greater than or equal to n, it will return the index out of bound error. Now next line of code is a loop that runs from index to n minus 2, and this piece of code essentially shifts all the elements that is right of the index to one element left, effectively overriding the target element. Now let's see this visually. Let's say we have to delete the element at 0th index in the array. So this function will take all the elements that are right to it and will shift one element left. Deleting the element from the front of the array is quite expensive. You have to shift all the elements to one step left. So it will be of big O of n time complexity. Now deleting the element from the end of the array takes constant time because the loop will run only one time and will delete the element. But on an average, deleting the element from any index will take big O of n time complexity. Now the next operation is inserting the element. So here we have the function insert that takes array, index and the value as parameters. Then similarly, n is the length of the array, and then there is a condition that will check whether index is out of bound or not. Now this loop will shift all the elements from the given index to the end one step to the right to make space for the new element. And lastly, this code will add the new element to the index. Now let's see some examples visually. Let's say we have to insert the value 15 on 0th index. Then we'll have to shift all the elements to one step right to accommodate the new element. This will be of big O of n time complexity because of the shifting. Now adding an element at the end of the array is a constant time operation because all you have to do is to find the memory address in the constant time and just assign the new value. Now inserting an element anywhere in the array will on average have a linear time complexity. Now the array is full and you cannot insert any more elements because it is static and cannot change its size. To address this limitation, computer scientists have invented the dynamic array, which can adjust its size as needed. Now let's see how a dynamic array works. Initially, suppose we have an array of size 2 with a base address of 100. Now we need to insert another element. The array becomes full and needs resizing. To handle this, a new array is initialized, usually double the size of the previous one. All the elements from the old array are then copied to the new array. The old array is deleted and the new array becomes the current array. This resizing process may repeat as needed. While resizing, we need twice the amount of memory each time to allocate the new array, resulting in a sequence like this: 2 plus 4 plus 8 and so on. And this will converge to big O of n, which would be the space complexity. Now time complexity will also be big O of n, because while resizing, we have to copy the elements from the older array to the newer one, so it will take big O of n as well. Now let's see the pseudocode for this dynamic array resizing. First, we start by initializing the array with a capacity of 2 in our example and setting the size to 0, which will increase as new elements are inserted. Now the resizing function takes the current array and its capacity as input parameters. First, it calculates a new capacity, which is twice the size of the older one. Then it creates a new array with this new capacity. Next, it copies all the elements from the old array to the new array, which requires linear time relative to the number of elements. After copying, the old array is deleted to free up the memory, and finally, the reference to the array is updated to point to the new array, and the capacity is updated to the new capacity. Now, when inserting the new element, the algorithm will first check if the array is full or not, and if full, it will first resize it, then will perform the insertion as usual. That's pretty much all about dynamic arrays. Now let's summarize all of these operations and their time complexities. First, for access and update operations, both are always constant time operations as they involve direct indexing into the array. And traversal will always take linear time as it requires looping through the entire array once. Now, the best case for insertion occurs when adding an element at the end of the array, which generally takes constant time, except when resizing is needed. In such cases, the insertion will take linear time due to the resizing process. But resizing is infrequent, so the process generally takes constant time. For the average and worst cases, insertion will always take linear time complexity because of the need to shift elements to accommodate newer insertions. Now, when it comes to deleting elements, the best case happens when the element to be deleted is the last one. In this scenario, the algorithm simply removes the element without shifting any others, resulting in constant time. However, in the average and worst cases, deletion will take linear time due to the need to shift elements. Now arrays can have multiple dimensions. Here we have an example of a one-dimensional array which contains base elements. Now this is a two-dimensional array, which is essentially an array of arrays. So for instance, if you want to access the second element of the first subarray, you would index it like this, where 0 means the first subarray and 1 means the second element within the first subarray. And this concept can be extended to arrays with n dimensions.